Hello everyone. I usually start with a little poll just to annoy Rich and make it out of context for his videos. Can you put your hands up if you are familiar generally with parallel file systems? Let's just see where we're starting off from, because I know some of you are GPU dudes. Okay, and who's actually got some kind of Lustre file system? And GPFS? And something else? Okay, so mostly Lustre in this room, probably about, out of the people who got Lustre, out of people who got a parallel file system, it's probably 60% Lustre, 30% GPFS, and then the rest have something else. So one more question. Out of those people who run Lustre, who has issues with some kind of file I.O.? Or who has a perfect file system and who has issues? Let's put your hands up if you have some issues with file I.O. in Lustre. Just one there. So nobody has, is it a metadata problem? Or small file problem? Or is it just you want it to go faster? Corrupted, okay. Well, I'm not going to talk about that at all. What I'm going to talk about is basically broadening the reach of Lustre based on the customer experiences we have. So I've got two main topics. One is, we often present Lustre and GPFS to customers, and there's often a push from customers to try and broaden the scope, because we all know that Lustres and GPFS are very good at large streaming I.O., but customers, particularly in bioinformatics and in general academia, in fact, when you've got thousands of students, somebody's going to have some small files, is they have some tricky I.O. And this can be random I.O., small file I.O. And then Lustre has a bit of an issue because it's not really well adapted to coping with lots of small I.O.s. There can be locking issues, and there can be issues with getting those small I.O.s onto disk, because the spinning disk isn't very efficient at putting those small pieces of data onto the drives. Because spinning disk does, so let's say a single nearline SAS drive does about 100 IOPS, and an SSD does about 30,000 IOPS, something like this. So there's a big difference. So spinning drives don't do very many IOPS. When it's small file I.O., we have an issue there. So we need to do some kind of caching. This is on point 1 up there. And the first part of caching problems is, how do we solve the read caching problem? How do you get data somewhere faster, like SSDs or in memory, such that you can read it in time for the application? So when the application's ready to read, it should be there sitting in cache. So you need some kind of intelligence to enable you to take the data from disk and to pull it into some kind of cache on SSDs or memory. So that's an issue that we're going to tackle today. The second problem we're going to tackle is the bigger, wider one. So over the next few years, we know, both from the big high-end US national labs and the big exascale customers, that there's problems in high levels of thread concurrency and high IOPS required for exascale class supercomputers. And that problem is also shared by the enterprise. So not only exascale supercomputers, but also right down to investment banks, things like this. So in relatively small in-memory databases, they also need to increase their ability to cope with high IOPS and high concurrencies. On point 2 there, or point 2.2, there's also the upcoming launch of various methods of non-volatile RAM. So today we have really one option, flash, but there will be more options. Maybe next year, maybe the year after, we'll see faster, lower cost options for non-volatile RAM, i.e. RAM where you can switch the power off and it stays there, like it's on a disk, like it's on flash. Okay, so that's the overview for my talk. I may or may not spend any time on this slide at all. Who is familiar with DDN? Okay, that's probably good enough for me to skip this one. We're currently about 550 people in Silicon Valley. We're quite big in HPC storage, and we also work in object and cloud storage. And I'm going to skip this one mainly, but I'll just give you a quick overview to put this talk in its place. So today, we have a portfolio that looks like this. On that side over there, I should use a laser rather than waving my hands in the air. On that side over there, we have an object store. So we're not going to talk about this today. The object store is a scale-out, peer-to-peer, distributed store for managing very, very large scale, kind of web scale data. But it's not a parallel file system. Over here, we have DDN's kind of core HPC class products, and they are, we're supposed to not say this, but they are kind of just RAID arrays, but fast RAID arrays. So they're designed for high-end HPC, and here's the big one here, the SFA12K, and here's a smaller one, SFA7700. Of course, inside these, we put various sorts of drive media, SSDs or spinning disk. And on top of these, we put file systems or analytics applications. Okay, so that's the current state of today. We have hardware, and then we use, so Exascaler is DDN's version and packaging of Lustre, GridScaler is GPFS, and then SAP and SAS and Hadoop, these are all analytics platforms we can also run on the same hardware. So I'm going to talk today a little bit about this up here, this little pink thing up here. It's slightly futuristic, so we're talking next year. So currently it's in sort of test mode. We ran a demo, which I'll talk about at Supercomputing 13. We have a number of customers out there running this in very early test mode. We're going to sort of roll out gradually a beta program over this year. And productization, the date for a product for this will come sometime next year. And it may be next year, we're not quite sure yet. SFX is the other thing. The other thing in pink I'm going to talk about is using SSDs or managing the use of SSDs today within existing file systems. So I'll talk both about something a little bit futuristic and something that's right here today. So this is a complex slide. FAdvise. Any hands? FAdvise? Anybody know what that is? Vague idea? 0. There's probably one, but maybe a bit shy. So FAdvise, POSIX FAdvise is a POSIX command. It allows an application or a user to specify to the underlying file system, give some advice about what it's about to read. So it can prioritize a certain piece of data. So if it's got a file or a directory structure and some data that an application is approaching, it can use the POSIX FAdvise command to tell the file system to move that into a higher layer of cache. So let's restate that. As an application's running along, it can send advice to the underlying file system to specify the regions of data which it's about to read. And that then enables the file system, if it's capable of it, of taking that data from spinning media, slow spinning media, and moving it into a fast SSD layer or into memory. So that's the fundamentals of what FAdvise does. The problem is, it's not really usable out of the box with Lustre, which is one of our major parallel file systems that we use. And the reason for that is, whilst Lustre does use ext4, and ext4 does support FAdvise, Lustre's a layer above that. So there's a gap in between the Lustre layer where the applications sit and where the files sit. So to be able to enable ourselves to give hints to the Lustre file system about data we're about to read, we need to do something else. So DDN engineers have been working in our labs on enhancing this FAdvise. So it's called LFS FAdvise is the patch we've got. LFS is a Lustre file system generic command. We've added some tweaks to it to support the FAdvise command. So if you read all that, basically the conclusion is we end up with something like this. And I explain this picture to you. So right to the top there, we have, just look at the big pink blobs. Right at the top, we have a client. Then we have a number of object storage servers. Then we have some storage at the bottom. And what we want to do is take data. So whilst an application is running along in time, before the application starts or before the application reads some data, we want to take some data from disk and raise it in the cache layer. So either to the object storage server memory or to the SSDs inside the storage, one or the other. And to do that, as you see, we've got multiple layers. We've got this sort of file system layer here running kind of ext4, and we've got the Lustre layer kind of sitting on top of it with the client-side LOVs, the object storage clients, and the object storage devices. But cutting a long story short, we provided a user space LFAdvise command so that the users can say, let's say a simple file name. So let's say I'm starting a job, and it's going to read a file called input. So then I would use the LFSAdvise command, specify the file named input, press return, and then advice gets sent through the Lustre layers to the lower layer saying the file input is about to be used at a certain priority. Let's have a show of hands. Am I making sense so far? Yes, you are. Nods, not hands, but good. So this patch is available now in the OpenSFS tree. You can have a look at it. It'll go into production at some point this year. Little caveat, today we've got some early results on this one. We've got the Lustre user group next week in Miami, and we'll have some more results. As always in a busy company, it's really hard to get results because you're busy talking to customers and we're trying to do benchmarks. So early results today, more results next week. And here's the benchmark setup, quite simple one. Let me go through this with you. So we're testing our LFS FAdvise command using this system. So we have, pressing the wrong buttons. We have a 7700. It's our smallest system. Does a maximum of about 10 gigabytes a second. We have 2 object storage servers, and these are just standard 2-socket Intel systems. And those are the object storage servers for Lustre. So this is a complete Lustre file system, and you might notice that we've hidden the metadata server inside this server because we were struggling for a few servers. Okay, so it doesn't matter, it's not a metadata test, but we've basically got a complete Lustre file system here. There's an IB switch connecting the Lustre file system to a single client. So early days, we've got a single client running some Lustre application. In this case, it's going to be the IOR benchmark. Here we go. And we're going to try and test out this LFS FAdvise command on top of Lustre using this simple system. The one thing we need to do is to clear the client caches between runs. So Lustre has a client cache. So because we're testing caching, we need to be really pristinely careful about how we clear caches in between these runs during the benchmark. It's quite tricky, in fact. Okay, so here's the early results. So in this test, we have a single node with 16 cores, and we've created a single job with 16 threads. And this single job with 16 threads is trying to do small I/O reads from a single shared file. So this sounds a bit artificial, but it's actually fairly similar to a common problem in bioinformatics where you have a reference genome file, and some of the quite badly behaved applications can read through that file one character at a time. So this does come up in HPC situations, and we've come across it quite recently ourselves. So we've got 2 graphs here, one with LFS FAdvise. So we're executing this command, and we're dragging the file into the OSS memory. So in this case, you haven't really spent any more money on hardware at all. All you've done is maybe spent some extra money on memory in the object storage servers, but at least you have some anyway, so you can just use that if you want. So 2 copies. Not very good with this button, am I? So 2 runs, the blue one and the red one. So the blue one is when we're doing small IOs, 4K, 8K, 16, up to quite large IOs, 1 meg IOs, to the disk subsystem. So we're basically doing those reads directly from a file that's lying on disks. In this case, a LUN comprising of 10 drives. And the second case is where we've executed the command, and we've taken that data, put it into the object storage server's memory, and we're reading it from there. And as you can see, there's something like a 3-ish fold speed up. And once we move it into the object storage server memory, we're basically hitting the LNet bandwidth barrier there for a single client, or close to that. It's not very well optimized, but it's, that's what we're hitting. So the first phase was to show that you can take advantage of your OSS memory using the LFS FAdvise framework and move data in there, really without spending any money. So I've left a diagram in here, so when you, I'll leave it up for a few seconds. This is kind of describing where the files are. So when you have small files, or lots of small files, you tend to have a stripe count of 1, which means you don't stripe the file across many object storage servers, because that have implications for metadata performance. So in this case, when we're reading from a file on disk, then it's actually on a single LUN, a single OST. So our file's spread across some disk like this. When we move it into memory, before the application starts, then it sits in RAM in the object storage servers. You'll notice there's a third option we'll be presenting next week, where we use the SFX feature of the 7700 to move that data, not into memory in the object storage server, but into SSDs in the storage system. The reason that is a good idea is because you have limited OSS memory. So you may just have a few hundred gigabytes, and you might want to have a few terabytes of cache. And using SSDs will allow you to do that. So we're presenting those results next week at LUG. So this is the first part of my talk. How long have I got? Into part 2 now. Another 10 minutes? Yeah, ish. Good. So with FAdvise, it's a user command. You can give it to the users, or you don't have to give it to the users, but you can then integrate it into your scheduling system. So if you take a scheduler such as Sun Grid Engine, who has Sun Grid Engine here? Or something like Sun Grid Engine? Okay, a handful. Who has LSF? A few, 1, 2, Slurm? Oh, a few of those? Okay. Anyway, these scheduling systems provide you a method, usually have a prologue script which executes before a job. So if a user specifies their input file when they submit their job into the scheduling system, then that framework allows us, the scheduler, to take the input file name, run FAdvise on it, and bring the data into memory prior to the job startup. So that's one example of how we can use this in a practical situation. There's more testing to be done than that. I would be interested in talking to customers who'd like to play with their scheduling systems using FAdvise. The most difficult thing to say in the planet. So that's one specific case. We just talked about read caching today to help accelerate small read IOs on files. But what about this next generation stuff I mentioned at the start? So how are we going to move in the exascale domain to take advantage of these next generation NVRAM systems? So IME is our approach. So who's heard of IME in this room? Throw up all the questions, just checking who knows what's what. So IME stands for Infinite Memory Engine, and it's our next generation software layer to take advantage of NVRAM for parallel systems. So you can see this diagram here. We've got this kind of situation today, but with a layer in between. So we have a Lustre or GPFS and parallel file system. We have some storage device. We have applications, and we have a POSIX API or something like this. What we've done with IME is insert this buffer cache layer in between the applications and the underlying file systems. And the consequences are supposed to be quite all-encompassing, so we should be able to do reads and writes, small IOs and large IOs, and work with aligned or random data. We also do that whilst providing data integrity and data protection, and we also manage the data such that when it moves through the burst buffer, it is reordered such that the data coming out down the bottom end to the parallel file system is pristinely reordered into nice, large, sequential aligned writes. So we're doing two things here at a high level. One is coping with lots of high concurrency, very high IOPS I/O, read and write. The second thing is, as we pass the data to a persistent file store underneath, we reorder that data, align that data, and then write it sequentially to the parallel file system. So there's kind of two major benefits at a high level. One is just faster I/O for all I/O types. The second is we get it to the persistent storage faster because we've made it behave nicely as far as spinning drives are concerned. This is how it works at a kind of reasonable level of detail. We haven't got enough time to go into super detail. So here we have the parallel file system, the back end, Lustre or GPFS, or could be something else indeed in the future. There's some file system metadata. And right at this side, we have a bunch of an exascale application, so a parallel bunch of threads running probably on many compute nodes attached to a network, which is ultimately attached via the burst buffer to the parallel file system. So one of the issues, if we take out this layer, is there's a lot of locking involved. So if we were to take this situation here and we just remove our burst buffer layer, these writes to, let's say we're writing to a single shared file again, this horrible problem which parallel file systems can't cope with very well, writing to a single file, then the first thread that writes the file to a certain segment will get a lock on that segment, and it'll write its 4K or whatever, and then the next file that wants to write another 4K will then have to get that lock. And this lock movement kind of serializes a problem, and it makes a parallel file system behave extremely badly. So rather than seeing gigabytes a second, you can see megabytes a second. We'll see an example of that. By having the I/O go to a burst buffer layer, we get around this kind of locking problem. The burst buffer itself is sitting in between the application and the file system. Neither the file system know there's a burst buffer there, and the applications don't really know there's a burst buffer there. But what the burst buffer does is it takes in the I/O, it protects it by spreading it using a erasure coding algorithm across many burst buffer nodes, which use some kind of flash or some kind of NVRAM. And from there, those I/Os which started off very segmented, very unaligned, can be put back into their parallel file system stripe format and then streamed to their parallel file system. So it's a very large caching burst buffer that A, alleviates a lot of the locking issues associated with many N-to-1 writes from large numbers of files into small numbers of, large number of applications, small number of files. And secondly, it cleans up the data and it drains it into parallel file system. And in the reverse manner, of course, we can accelerate reads. So that's just writes. So sort of 2 points, manage very strange, bad behaved I/O and stream it down to disk. We do it whilst maintaining whilst protecting the data with some kind of erasure coding algorithm across the burst buffer nodes. And for reads, the similar situation happens to happen before with FAdvise. We've somehow got to add some intelligence to allow the applications or the scheduling system or something to move data prior to its being read into this caching layer. So in this case, we have a bigger cache. We have a distributed SSD or flash or NVRAM or next generation NVRAM layer on the network somewhere in between the file system and the applications. Nevertheless, it's the same problem. We have to give some intelligence to the file system so that she can move data in advance into this caching layer. So both reads and writes are satisfied, and we do it whilst protecting the data with IME. Yes?
So you say it's between the file system and the application that sits on the client level or sits on the I/O server level, because the file system is represented by clients, network, and I/O servers. So where it sits.
Yes, you're absolutely right. So if you think about it, it must sit both at the client level and at the server level. So the I/Os are writing to a client. The client's doing something clever and writing to the server side of IME. So we've got a client IME client and an IME server side. So one sits just like your Lustre client would directly underneath the applications, speaking POSIX to the applications, taking the I/Os. And when it's got the I/Os, it writes those into the burst buffer server layer. Now the server layer could be a separate distributed set of burst buffer nodes on the network, or it could be in the client as well. So it could be SSDs or NVRAM in the client. So we tested this at the demo at Supercomputing, 5 minutes, perfect. So what we had is a bunch of Dell nodes. I think there was 14 1U servers with FDR InfiniBand. We had again a small system, a 7700, with 60 drives inside it. We connected to this one was actually using GPFS as a file system, not Lustre in this case. And there's 2 file servers, so kind of similar to my previous situation with Lustre and FAdvise. And what we do is a number of runs to do basically with and without the burst buffer layer. So with the burst buffer layer, if we just look at this graph here, if I can manage to click the right button more than once, then we have a 4K strided write. So 8 meg strided write's beautiful. So nice, lovely, aligned, big block I/O writing from this cluster of 14 nodes, that's a total of 100 odd threads, writing over InfiniBand into a GPFS file system in which we've populated with SSDs. So I think it's 24 SSDs, something like that. Okay, so this is an SSD-populated GPFS file system. It goes really fast. It's very good. But that's because it's streaming I/O. If we do exactly the same thing, but use 4K strided writes, then there's a dramatic drop from 43 gigabytes a second to 17 megabytes a second. And that's not because SSDs are bad, all of a sudden. It's because there's a huge locking issue in the parallel file system, and we've serialized the process, and we're passing these locks between the client threads as they try and do their 4K writes. And that's quite disastrous, as you can see, from 43 gigabytes a second to 17 megabytes a second with the same hardware. With IME in the way, and let me just describe how we did this. So we took the SSDs out of the GPFS file system. We put them in the compute nodes. We put just standard nearline SAS drives back in the underlying storage. We've got to have some storage there. And the SSDs went, instead of being in here, went over here in the clients. And then we installed IME. We had the client on each of the servers, and we also had the server side in each of the servers using the local SSDs as the physical burst buffer layer. And then we drained it down to the GPFS file system as a second stage. And then we accelerated from 17 megabytes a second with IME. As you might expect, we've taken out the locking, and now we're back to basically streaming I/O. Doesn't matter, it's 4K or 8 meg. SSDs don't mind, they love it. So we get back to our 49 gigabytes a second. Oh, dear me. So obviously there's some nice marketing number here, 200,000, 808,000% increase. So this is kind of a significant benefit. Obviously it's a very particular case. We've got lots of threads talking to a single shared file. It's kind of disastrous for conventional parallel file systems, but you can see the benefits here. The other part of this, which is for me sort of more interesting, is that when we then drain the data from the burst buffer layer into the physical disks, then we achieved 4 gigabytes a second from the same data. So by taking the data, realigning it, basically putting it back into a single parallel file system stripes and writing those sequentially into the spinning disk, we get back up to 4 gigabytes a second. So two things we've done. One is, at relatively low cost, massively improved the performance of a many-to-one small write situation. And the second thing is, we've also improved that as it moves down to the underlying spinning disk-based parallel file system. So the summary for IME is it's not here yet, but we are interested in hearing from people who'd like to be beta customers for this year. We expect it to be quite generic, so we're hoping to support more than one parallel file system, common parallel file system, and also support reads and writes. It will benefit not only the small I/Os and the 4K random reads, we also expect, given the new hardware in NVRAM domain, to get speed-ups and different shapes of architecture available in terms of overall parallel file systems. Okay, here's my summary. We've talked about two things. One is kind of relatively simple and available today. It's a patch we've developed for Lustre, LFS FAdvise. We're presenting more about it next week at LUG, which helps us pass hints through the Lustre file system to the storage system, so the storage system can then move data into memory or into flash. And the second thing I've explained is our next generation IME system, which we'd be interested in talking to you about under NDA and interested in looking for beta customers. Thank you.